Okay, so this is section 8.2, testing the difference between your means for small independent samples. So in this section, we are going to be doing the t-test with 2 samples, okay? So what you want to make sure that you know is you don't know your population standard deviation, okay? Your samples need to be random. They also need to be independent. The other key is that your populations must be normally distributed or your sample sizes have to be greater than or equal to 30, okay? So the key difference between your Z and your T, we're gonna go over, but your sample size is one of the key differences between the two, and whether or not you know your population standard deviation. Okay, so here's our formula. It looks really, really, really similar to the Z formula that we used for section 8.1. And your standard error, which is here in the denominator of your fraction, is going to depend on your degrees of freedom and your population variances as well. Okay, so we have 2 formulas. When the variances are equal, we're going to be using this formula here. Now, it's not always happening that they're going to be equal. So if the variances are not equal, we're going to be using this formula here. Okay. So, and I'm going to show you. I'm going to show you what I mean with that when we run through an example, because I know I'm throwing a lot of formulas at you right now. So essentially, what we are going to do when your variances are not equal is your degrees of freedom is going to always be the smaller sample size. And you're going to use this formula for your standard error. So I really like this graphic, and this graphic is on page 443. Okay, so the first question that you have to ask yourself is whether or not you know your population standard deviation. If the answer is yes, and the question is then, are the populations normal, or are your sample sizes at least 30? And if they're at least 30 and it's normal, bam, we can use Z. And if it's not normal, or at least 30, then you can't use either of the tests. All right, so if the population standard deviations are not known, then the question is, are the populations both normal and both have a large sample size? And if the answer is no, then we can't use the test. Or if it's yes, then the next question is whether or not your variances are equal for the population. If it is equal, we're going to be using the t-test with this formula here. And if they're not equal, we're going to be using this. Okay, so let's run through the words. And then we're going to run through a couple of examples, okay? So first, verify that your standard deviations are unknown. Verify your sample sizes. Then we always state our claim, and then identify our null and our alternative hypothesis. Specify your level of significance, that's your alpha. You're then going to determine your degrees of freedom. So we have 2 different formulas. In this case, whether or not the variances are equal or not equal. And then to determine your critical values, you're going to use table 5 from Appendix B. This is going to be on page A18. Okay. And then determine your rejection region. Find your standardized test statistic. And then from there, you're going to make a decision whether or not to reject or fail to reject. And then you're going to interpret that decision in the context of your original claim. Okay, so let's go ahead and do an example all the way through. So we have the results of a state test for random samples of students taught by two different teachers at the same school are shown below. Can you conclude that there's a difference in the mean mathematics test scores for the students of the two teachers? Our alpha level is 0.10. Assume the population populations are normally distributed, yay, but the variances are not equal. Okay, so our population variances are not equal. So that's going to help me determine which formula I'm going to end up using. Okay, so the first thing that I always like to do when I start these problems, as you all know, is identify my claim. So the claim is we are trying to figure out, is there a difference? Meaning, are my means not equal for these two teachers? Okay, so the complement to that is going to be that mu1 is going to be equal to mu2. All right, so let's identify our null. Our null in this case and our alternative is our claim. Okay, so in this case, they told me that my variances are not equal. Okay, so when my variances are not equal, we need to use our smaller n to determine our degrees of freedom. So in this case, the smaller n here is from this first teacher, which is 8. That's a super small class, isn't it? So my degrees of freedom is going to be 7 because I'm going to do 8 minus 1. And then the other thing to note is we are doing a two-tailed test, and I know that because my null hypothesis is equal to. So since we are doing a two-tailed test and my alpha level is 10%, 0.10, I'm going to look at page A18 and I am going to find my T critical value with 7 degrees of freedom is going to be, so T naught is going to be equal to plus or minus 1.895. All right. So now that we have that, that is telling me that my rejection regions are going to be either less than negative 1.895 or greater than 1.895. Here. And here. Okay. All right. So since our variances were not equal, we need to use the standard error formula that looks like this. So S all right, there we go, is going to equal this, that's a 1, this is squared, plus S2 squared over N2, and all under the square root. Yep, okay. So I'm going to go ahead and put in the numbers for my chart here. So we're going to end up with, still thinking, 39.7 squared divided by 8 plus 24 squared. All under your square root. Okay, so if you plug all that into the calculator, and do be careful if you're typing everything all once, I would definitely use parentheses around each of these fractions here. You will end up with 15.178. I usually, when I do this, round to 3 decimal places, just because I feel like that gives me a very good number and it helps me be more accurate than rounding really a whole lot. Okay, so now that we have that, we're going to find our T test statistic, and I'm going to use the following formula. So T equals x1 minus x2 minus all divided by my standard error that I just calculated. All right, let's plug in. Okay, so from the chart, we know that we have x bar 1 is 473. Minus 459. All right, our null hypothesis is saying that our means are equal. And if our means are equal, that's going to end up 0 when we subtract. And then we just calculated this. It was 15.178. Okay, so if I plug all that in, I'm going to end up with a t-value for my test statistic as 0.9224. Okay, so let's see. Is that in my rejection region? And the answer is no, it is in the middle here. So that means I'm going to fail to reject. Well, that E is just laying down on the job, isn't it? Okay. All right, so I'm going to type my summarizing sentence now. Oh, that is not what I'm doing. I'm typing. Okay, so we're going to say there is not enough evidence to support the claim that the means are different. Okay. All right, so let's do another one. All right, in this problem, we have the annual earnings of 15 people with a high school diploma and 12 people with a bachelor's degree or higher are shown below. Can we conclude that there's a difference in the mean earnings based on our level of education? We're using a significance level of 0.01. Assume that populations are normally distributed and our population variances are not equal. Okay, so this one is very similar to the last example. So what I actually want you to do is I want you to pause, work through it, and then I want you to push play. Okay, so hopefully you paused it for real. So our claim is that our means are not equal. So the opposite of that is going to be that they are equal. Oh, that's for B2. All right, so null is here. Alternative is my claim. Okay, so this time we're going to be using the 12 to determine our degrees of freedom, and our degrees of freedom is going to be 11. And then we are using a 1% significance level. So 1% significance level with degrees of freedom of 11 is going to give me a T0 critical value of plus or minus 3.106. So if I draw my little bell curve here, we have rejection region of less than 3.106 and greater than positive 3.106. Okay, so, and again, this was a two-tailed test. I'm not sure if I mentioned that before. Okay, so since our variances are not equal, we're going to be using the same formula to calculate our standard error like we did last time. So I'm going to write it down because you know that's what I like to do. Oh, I did a good job of writing that. Okay, let's see. Two, 3, 1, 8 squared. Oh, that's a squared. 15 plus. All right, cool. So if I plug that into my calculator, I'm going to get 155.416. All right, so now we're going to use our T formula. We're going to plug everything in. Find that test statistic. So x bar 1 minus x bar 2. Minus mu1 minus mu2. Whoop. Minus. All right, so let's see. We're going to do 27,136. Is it 3? Minus 34,000. 329. Okay, minus 0. And if I plug all that in, I'm going to get negative 4.63. All right, so bam, is that my rejection region? You bet. Okay. So we are going to reject the null, which means in this case, there is evidence to support the claim. Okay, so let's go ahead and write our sentence. Okay, so there is evidence to support the claim. There is evidence to support the claim that the means are. Okay, so it's been a lot of fun writing down all these formulas, and it's taken me quite a bit of time. So wouldn't it be great if we could actually do this in the calculator? And the answer is, yeah, it would be so great. And I really wish you would tell me about this. Okay. So our calculator steps are as follows. We are going to first hit stat, and then you're going to go over to test, and then you're going to go down to to SAMP t-test. And then the big thing it's going to ask you is whether or not, I just wrote poop. it's pooled or not pooled, and pooled, remember, is going to mean that you have the same population variance. Okay, so if it's not pooled, then they don't have the same population variance. Okay, so let me go ahead and read the example now. So we have a manufacturer is claiming that the calling range in feet of its cordless telephone is greater than the leading competitor. You study this using 14 selected phones and 16 similar phones. We have an alpha level of 0.05. Can we support the manufacturer's claim? Assume the populations are normally distributed and the variances are equal. Ooh, yay. Okay, so the first thing we're going to write down is our claim. So in this case, we're saying that the one mean is greater than the other one. And our complementary statement would be that it is less than or equal to. So in this case, this is my alternative, and this is my null. Okay? Okay, so from there, I'm going to type everything into the calculator. So I'm going to hit stat, I'm going to hit test, and then to sample t-test. And then so you have the option to do data or statistics. And in this case, we have statistics because we have all the information. And then you're pretty much just going to type everything in that you have. And then you're going to go down to the where it says mu1 is not equal to mu2 or less than mu2 or greater than. So you're going to pick whichever one is the alternative hypothesis because that's what you're testing in this case. And then you're going to hit calculate. And from there, it's going to give you a t-value and a p-value. So in this case, I'm getting a t-value. My test statistic is 1.811, and my p-value is 0.0404. So in this case, we're checking to see the relationship between the p-value and alpha. And in this case, the p-value is going to be less than alpha. And what do we do when the p-value is less than alpha? We reject. Okay, so I can write my sentence now. So there is enough evidence to support the manufacturer's claim. Okay. And you can get more specific with this as well. All right, let's do another one. I want you to try this one. Okay, so it's very similar to what we've just done. Okay, so hopefully you gave this one a shot. So we have a manufacturer claims that the watt usage of its flat panel monitors is less than that of the leading competitor. Okay, so in this case, our claim is that U1 is less than U2. Okay, so then the opposite or complement to that would be that mu1 is greater than, that's not a greater than. Okay, so we're going to identify our alternative and our null. Okay, and then another key here, it says the population variances are equal, which means this is a pooled test. All right, so I'm going to go ahead and type all of that in, and when I do that, I'm going to get a t-value for my test statistic as 3.997. Oh, that's not a 7, sorry. Okay, and I'm going to get a p-value of 2.49 times 10 to the negative fourth. All right, so P is way, way, way less than our alpha, 0.1. So we're going to reject. Okay. All right, and so there is enough evidence to support the claim. All right. The last thing that we're going to do is we're going to find a confidence interval using this t-test. So again, I'm going to use my calculator for this. So what you're going to do is you're going to hit stat, and then you're going to go over to test. And then you're going to go to samp t int. Okay? What that stands for is 2 sample t interval. Okay, and so once you go there, you have 2 options again to do data or statistics. So in this case, we're going to be doing statistics. And so then you're going to type everything in, and we're going to go down to the C level. That stands for confidence level. So in this case, it's 95%, so it's 0.95. And then pooled, again, that means if your population variances are equal. And since they told me that right up here, it says assume that the first population variance and the second population variance are equal. So I'm going to say yes for pooled, and then I'm going to click calculate. And from there, it's going to give me an interval. And so my answer for this is going to be negative 0.8826 and 0.08259. So if you were going to say a summarizing sentence, you would say with 95% confidence, the difference in the population mean for these 2 samples is in the interval of blah, 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 blah.